FEE 441A, 541A. Homework number 2 is due in a week. That's the 21st. Exam number 1 is going to occur a week from Friday. And lab number 1, you probably want to start thinking about it, looking at it, maybe even working through the pre-lab at least before exam number 1, but it's not due in terms of dropping it into the Dropbox. And you only need to submit 1 submission per team into a Dropbox, and that's due on the 3rd of October. What I want to do today, and going around are just some sheets as a reminder of how you have teamed up, and if you haven't selected a team, you might put your name on a row, and on the D2L website in the module labeled lab number 1, we should have the teams posted, and you should also see this matching of teams to the system. When you go into the lab, you will be asked, or you will be assigned, based on that matching, a particular spring. You may have to physically remove one spring and introduce a different spring, spring 1, 2, 3, or 4, and then it will also tell you how many masses. Each of these masses is half of a kilogram, and whether you're assigned 1, 2, 3, or 4 masses, that will be how many you put on the carriage or the cart in the system. Question? And the schedule time, it's just to show you what's available. It's essentially a sample. You don't have to sign up today during class. That you can go sign up with, I hope, at the stock room, but that basically shows you any time slot is available other than the class time. If you're going to be doing control during that hour, I would like for you to be here, and then on your own time you can do the lab, is what I'm wanting to happen. Today what I want to do is work through a vector linearization example. We looked at a scalar case where we had a first order system, and we may get into system identification, which is the precursor to lab number 1. In lab number 1, the system that you will be identifying is second order. We'll start by just looking at a first order system identification, and then we'll progress and start looking at systems that are second order and underdamped, and how do we then model those or come up with a strategy for identifying the transfer function. That's what I'm meaning by system identification. As a starter, with this linearization process, we have a nonlinear system, which means this function f is a nonlinear quantity in terms of the state variables and the input. The x0 and the u0, and remember, x0 and u0 could be vectors. x0 and u0 actually satisfy that nonlinear equation, that dynamic system. That's a nominal solution to that system, and we are linearizing around that nominal solution. This we should have already covered in the last lecture, but this now lays this linearized system dynamics in front of us for a second order system. If it was a third order system, then what would your A matrix look like in terms of size or dimensions? It would be 3 by 3. It would now have 9 elements and 9 partial derivatives. With a second order system, our system matrix is square, it's 2 by 2, and it's a collection of these 4 partial derivatives. And once you do the partial differentiation, you may end up with just numbers. You may end up with expressions that are functions of the x's, the different coordinates, x sub 1, x sub 2, x sub 3, and the u's, u1, u2. You substitute for those x's and u's the nominal values for those quantities that actually satisfy the governing nonlinear differential equation. Consequently, the A matrix, in this class it will be constant, but in general it could be a time-varying matrix, A of t. as a function of the x naughts and the u naughts. The input matrix is the same. You might end up with x's and u's sprinkled around after doing the partial differential equations, but you get rid of those by replacing them with these values for x naught and u naught. That will, I hope, become clear through the example. And in this example that I've illustrated, the input I just assumed was scalar. But you could have 2 inputs or 3 inputs. Let's say you had 3 inputs for a second order system. What would the resulting B matrix be structurally or dimensionally? How many rows would it have? If we have a second order system and 3 inputs, what are the rows of B? How many rows? If it's second order, how many rows do we have? So if it's second order, we just have an x1 and an x2, and it has to be, the B has to be compatible with that right hand or the left hand side of this system of equations. The B matrix would have 2 rows and how many columns? It would have as many columns as we had inputs, so it would have 3 columns. The B matrix would be 2 by 3 if we had a second order system with 3 distinct inputs. So the B matrix can be something other than just a column matrix. It's a column matrix. Why? Why would it be a column matrix? Why would B just be 2 rows tall and 1 column wide? What dictates that? It's a trivial answer. You only have 1 input in that case. All right. So let's look at a particular second order system. Suppose now we have an x double prime. You could think of that like an acceleration, and you've moved everything else on the right hand side. And what's on the right hand side need to be state variables and the input. And maybe you've already caught the typo. So I need to close the functional argument on G. But on the right, we have some nonlinear expression involving x, x prime, and u. For our example, let's just, and I may just eliminate the argument t. We're in the time domain since we're differentiating with respect to time. Let's say on the right-hand side we have 4x plus 6x times x prime. There's a nonlinearity because we have 2 of our state variables multiplied together, minus x prime squared. There's another nonlinearity, plus all of this is on the right hand side, u x prime. There's another nonlinearity, quit it, plus 5u. And all of this is our G. That's a function of x, x prime, and u. And I hope that it's clear that that's not linear in x, x prime, and u because of these cross products or these products of state variables and inputs. Now, what we want to do is first put this into a form that will give us a second order or a coupled set of first order differential equations. Meaning, we want to quit dealing with x and x prime and x double prime. Let's say we want to define our states to be z sub 1. How many state variables do we need if we're trying to put this into like a state variable formulation? 2. It's second order, so we need a z sub 1 and a z sub 2. Let's just go ahead and define z1 to be x, and let's go ahead and define z sub 2 to be x prime. we're doing that to put this into a state space form, but it will be a nonlinear state space form. Until we linearize. If we now have defined z1 and z sub 2, we now want to find a z1 prime equation and a z sub 2 prime equation. z1 prime, since we define z1 to be x, that's simply x prime. And can we rewrite x prime in terms of z1, z2, and u? Since we defined z2 to simply be x prime, that's all that this is. And in fact, this is now our first right-hand side. This will be f sub 1, that's a function of z1, z sub 2, and u. That's sort of the trivial case, but sometimes you stumble on this. You go, I don't even know what I'm doing, but you're now just creating a right-hand side. The second one, the z sub 2 prime, is now x prime prime, or x double prime, and that was what the original differential equation was equal to. And so now we have that is going to be equal to 4 times x, but we relabeled x as z1. Then we had 6 times x prime. That will now become plus 6 z1 z sub 2. Then we have minus what? Z sub 2 squared. We now have minus z sub 2 squared plus u, which was multiplied by x prime, which is z sub 2, plus 5u. And this mess is our f sub 2 of z1, z sub 2, and u. And it's important that we now have identified f sub 1 and f sub 2 because that's what we need to start doing these partial derivatives, to fill up our system matrix A and our input matrix B. We've now rewritten our second order differential equation as a set of coupled first order differential equations. We have a z1 prime equal to an f1, and we have a z sub 2 prime equal to an f sub 2. And if we go back to what we said each of these needs to be, do you see now how we're going to use the f's, f sub 1s and the f sub 2s? Those are going to help us create the A matrix and the B matrix. We now need to find our top row, or what does delta, in this case z sub 1 prime, what does delta z sub 1 prime equal? That's now going to be all of these partials of f1. So we now have the partial of f1 with respect to z1 evaluated at z1 equal to z1 naught, z sub 2 equal to z2 naught, and z sub, whoops, falling asleep, and u equal to u naught. And we haven't yet determined what those u's and z naughts are going to be, but they have to satisfy this original differential equation. But this is now multiplied by this small variation in Z1, Z1 minus Z1 naught, but that is really just what we're calling delta Z1. So we now have a delta Z1 prime equal to some mess times delta Z1 plus partial of F1 with respect to Z sub 2, again evaluated at Z1 naught, Z2 naught, and U naught. It now gets multiplied by Z sub 2 by minus Z sub 2 naught, which is just delta Z sub 2. And finally, we take the partial of F1 with respect to U, evaluate that at these operating conditions that satisfy the original differential equation, times U minus U naught, but again this is equal to delta U. And if we do the exact same thing for our second equation, it has exactly the same structure. We just have to keep track of the different f sub 2's and their partials. Meaning, if we look for an expression for delta z sub 2 prime, that's now equal to the partial of f2 with respect to z1, evaluated all of the nominal conditions, z1 minus z sub 1 naught, but that's just delta z1, plus partial of f sub 2 with respect to z sub 2, times delta z sub 2, plus partial of f sub 2 with respect to u, delta u. That's the structure. Now we can perform all of those partials because we know what f sub 1 and f sub 2 are in terms of the z's and the u's. What we don't yet know are these nominal operating conditions. The z sub 1, or z sub 1 0, the z sub 2 0, and the u sub 0. In that case, what we're really after is a set of z naughts and u naughts that satisfy the original governing nonlinear differential equation. And in this class, most of the time, if not all of the time, that's going to be an equilibrium point. If you think of a pendulum that's swinging in the downward position, what's its equilibrium state? Vertically down. So we're linearizing, we're finding what are the angles and the velocities, angular velocity associated with that pendulum in that equilibrium condition. Question? Yes, so this notation, the question was all of these partials of f sub 2 are evaluated at the nominal operating conditions. So my shorthand, I got tired of writing, this 0 actually means z sub 1 0, z sub 2 0, and u sub 0. That's what I was meaning by /0. And what we're trying to do now is determine some or a particular set of these operating conditions for this particular system. And if we just then think of it like this pendulum, then we're really looking at what is the equilibrium condition. Or let me just try to write this out. Many times it is an operating point And we are looking for values of Z1, Z2, and U when Z1 prime is at equilibrium. Z1 prime would be 0 and Z2 prime would be 0, which forces F1 of Z1, Z2, U to be 0 and F sub 2 of Z1, Z2, U to be 0. In this particular case, what did we have? We had our F sub 1 of Z1, Z sub 2, and U equal to 0. Or it was actually equal to Z sub 2. If we go back, F sub 1 was equal to Z sub 2. And if we set F sub 1 to 0, what does that force our nominal condition to be? So our Z sub 2 is nominally going to be 0. Our Z sub 2, 0 at the operating or equilibrium condition. If we now looked at F sub 2, and if we now said, what is this going to be at the nominal operating condition, we're setting that equal to 0, or we are now forcing this mess to equal 0. And we've already found from F sub 1 that Z sub 2 is 0. So everywhere we see a Z sub 2, we replace it with 0, and a lot of things go away, don't they? The three middle terms are now gone. And now we need 4Z1 plus 5U to equal 0. And one such condition would be to just set Z1 to 0 and U1 to 0, and then we have everything being 0. Just like the equilibrium being down, we have the angle is 0 and the velocity is 0. And we're linearizing about that position. In this case, F sub 2 being 0 is going to then imply, since we've already found that Z2 naught is 0, Z1 naught is 0, and U naught is 0. But there are other possibilities, but let's just use these in this example. These are the values now that we substitute in when we have some non-zero expression in these partials. What was the partial of F1 with respect to Z1? This was the partial. F1 was Z sub 2, and we're differentiating that with respect to Z1. That's going to be 0. If we now take the partial of F1 with respect to Z sub 2, when F1 was just Z sub 2, that's now 1. Third week or fourth week of class. Still looking for the right room. Ouch. Partial of F1 with respect to U. Partial of Z sub 2 with respect to U. That's 0. Now we can start doing our F sub 2's. Partial of F sub 2 with respect to Z1. This is now, I don't want to write all of what F2 is. Let's go back and just look at what F2 is and differentiate with respect to Z1. If we take the partial of this right-hand side with respect to Z1, what do we end up with? 4, 6Z sub 2, and that's it, isn't it? That's the only place we have a Z1 and we're differentiating with respect to Z1. This partial now becomes 4 plus 6Z sub 2. The partial of F sub 2 with respect to Z sub 2 6Z sub 1 minus 2Z sub 2. Did you take your Dramamine this morning before class? I'm sorry, I'm sliding back and forth. You just close your eyes when I'm sliding, and then it will be fine. And then I'll say, open your eyes. That's maybe cheer 3, right? Close your eyes, open your eyes, close your eyes. Open. We're playing peekaboo this morning. Now we're going to have all sorts of students walking in. Where were we? We were at minus 2Z sub 2 plus U, thank you. And that's it, right? And what about partial of F sub 2 with respect to the input? Close your eyes. Open them. We now have Z sub 2 plus 5. Close your eyes. Plus what? 5. Now, what we need to do is we need to evaluate all of these partials at the nominal operating points, which were all zeros. Which means anywhere we have a Z1, a Z2, or a U, we replace those with zeros. In this example, in general, maybe Z1 naught might be pi over 7, just as an example. Then anywhere you saw a Z1, you would replace that with pi over 7 after you've taken the partials. Is that clear? In this case, everything sort of starts dropping out. But we end up with, then, the following. We have a delta Z1 prime, a delta Z sub 2 prime, equaling partial of F1 with respect to Z1, evaluated at the nominal conditions, that was 0. I'll go slow. Partial of F1 with respect to Z sub 2, at the nominal, that's just 1. Were there any partials of F1 with respect to U that were non-zero? No, not on F1, was it? Because F1 was just Z sub 2. So now in the second row, now maybe I can almost squeeze it all in. What do we have in the 2-1 entry of our system matrix A? What value? 4. What value do we have in the 2-2 entry of A? And what about in the second row of our input matrix? 5. This is now our A matrix, or our system matrix, and our input matrix B. And now you can ask the question, what's the dynamic behavior around this nominal operating condition? We're basically at 0, 0, 0 for our nominal operating condition, and we want to know if I got perturbed or bumped a little bit off of that, what would my dynamic behavior be? Would I go back? So if you took a pendulum and you nudged it, it would naturally want to just come back to that equilibrium. What if the equilibrium condition that we were linearizing about was upright vertical, and now you tap it? Now it's not going to go back to that equilibrium point, is it? That would be an unstable equilibrium condition. The downward would be a stable equilibrium condition. We want to see, after we've linearized this nonlinear, second-order nonlinear, what are the natural dynamics around this nominal condition, operating condition of 0, 0, 0? How can we find that? How do we find the natural dynamics of a given system? And here we're after the natural dynamics of the linearized system, which means we're really looking at capital A and capital B. Which of those tells us dynamic information? Or do they both? So if I gave you a transfer function and I said, what does this system's behavior look like, or can you describe the system behavior resulting from this transfer function, what would you start looking at to give me a feel for how this system is behaving? Poles, right? You're looking at the poles, the denominator, the values of S that cause the denominator to vanish. In this state space representation, what is the same as the poles in our transfer function? The eigenvalues of that system matrix A. And here, they're not on the diagonal, are they? And we don't have a diagonal matrix or an upper triangular or upper or lower triangular, so our eigenvalues are not on the diagonal. Question? Where did I get the 4, 0, and 5? Just right there. So the 4, 0, and 5 came from evaluating these partials at the nominal operating conditions. And the nominal operating conditions that we selected for this example were 0, 0, and 0. Z sub 1, 0 was 0, which makes that 6 in the right go away. Z sub 2 is 0, which gives us just 4 remaining in the partial of F2 with respect to Z1, and it only gives us a 5 remaining in the partial of F2 with respect to U. And the partial of F2 with respect to Z2 just was annihilated by those zeros for those nominal conditions. Now, did that answer your question on 405? So now that we're on the 405, sorry, that's a highway, isn't it, in LA somewhere? Oh, boy. Where were we? Natural dynamics. We're looking for the eigenvalues of our system matrix, which are the eigenvalues of A. And we can find those by looking at the determinant of lambda I minus A and setting that equal to 0. Where the lambdas, the values of lambda that cause this expression to be true, will be our eigenvalues. In this case, we have lambda minus 1 minus 4 lambda. You guys did this in math or in ECE 310, didn't you? Or math 310, or whatever math you took. Now, how do I find the determinant of a 2 by 2? And you have to know this by the exam if you don't already. This is the product of the diagonal minus the product of the off diagonal. And now we see that we have lambda squared equal to 4. So now we have 2 roots, 2 eigenvalues, plus and minus 2. And where did we want those to be living if we wanted it to be stable? We wanted all of their real parts to be negative. Is that true? No, we have one that's at plus 2, so this is actually an unstable for our natural dynamics. And you could then sketch this if you wanted to. Here is our S-plane. Here's the real part of S, and here's the imaginary part of S. And where would we put, now poles are our X's in the complex plane. Where would our poles be? On the imaginary axis? Do they have an imaginary component? No, those eigenvalues were purely real. We had one at -2, and we had another one at +2. And all it takes is one such pole in the right half plane to cause everything to be unstable. Meaning if you now looked at the modes associated with these two poles, this guy in the time domain would be giving rise to an e to the plus t, and this pole would be giving rise to an e to the -2t. Even though you have an e to the -2t, it gets dominated by the e to the 2t in your behavior. So if you nudged this nonlinear differential equation away from 0, 0, 0, it's not coming back to 0, 0, 0. It's unstable, that equilibrium condition. If you wanted it to come back, stay tuned. That's why we're going to be designing controllers. We're going to try to design controllers that will pull that unstable pole at +2 into the left half plane. That's why you're taking this class. Open loop, it's unstable. We'll put in a controller and close the loop, and we'll now be able to pull those unstable poles into the left half plane. Get them out of the right half plane. Questions on linearization? Now we're ready for system identification, and now we do need our eyes to be wide open because we're trying to identify a system. So let's look at system identification. If I said you had a first-order system and you applied a constant to that first-order system, what would its response look like in the time domain? So here I'm going to say first-order response due to a step or constant input. I'm going to say my output of that system is y, and now you apply a constant to that, and it's first order. Do you have any clue what the response looks like? If you apply a constant to a first order system, what if I gave you an RC circuit and said apply a constant voltage to this RC circuit? What would you expect the capacitor voltage to be doing? Did everyone hear that? I'm just going to assume that I heard that. It's going to grow, isn't it, exponentially, and eventually stabilize at some final value. Meaning out here, we might call that some constant A1, which is the final value of our output, y sub fv. Can we collect any other useful information from this picture besides the final value? And that should have been exponentially close to that dashed line. I just can't draw. So it's approaching that dashed line. Can we extract any other useful information about the system's behavior from this picture other than its steady state value? The time it takes to get there. And now you can say, oh, well, let's get within 1% of my final value, and that would be our settling time, a 5 time constant settling time. We might say then that that's occurring right here. That's now t sub s, and that particular length of time is 5 tau for a 1% settling time. Now we have a final value and a time duration to get close enough to that final value. And really, those are the only two data points that we need, other than what value of constant did you apply to the system. That's all we need to actually extract a transfer function for a first order system. What's a first order transfer function look like? Pardon? Did I hear that? 1 over s minus a. Is that a well-behaved system? Would that lead to what we just drew? Is it stable? What value of s causes that denominator to vanish? A. Where is a? It's in the right half plane. So let's change that. So now we have 1 over s plus a. That's a generic first order, but that's not as generic as we could make it. That's a pole, but we need to maybe adjust the DC gain value. And so the way that we are going to do that is we are going to factor out the a so that it doesn't mess up with our numerator value. And we're going to then say, let's just parameterize a first order system to identify it. Let's just call that some gain alpha and then tau s plus 1. Meaning, if we had a beta up here, that would give us a different gain, and we could now factor out the a so that we have an s over a plus 1 and a beta. And now do you see that alpha is beta over a and tau is 1 over a in the first order model that somebody gave us before? But this one is the one that we will use because what's the DC gain of that transfer function? Alpha. It's the value of g of s when s is equal to 0. S equal to 0 is DC, isn't it? As the frequency gets bigger, then we get this j omega, that omega is now bigger in frequency. But at DC, we're evaluating this at s equals 0, and that way our denominator is well behaved, and we get our DC gain immediately identified as alpha. And our time constant is tau, and how is that related to our pole based on the factored form that we see up above? Tau is now 1 over a, isn't it? So if we have a faster system, our time constant is going to be shorter. If we have a pole that's really far into the left half plane, it's fast. If it was at minus 10, then a would be 10. And what would our time constant be? 1 over 10. So in 5 time constants, 5 over 10, or half of a second, our system would have already reached steady state. So if you have a pole at minus 100, now your settling time is one over that, or 0.01 seconds, and now 5 time constants, 0.05, You have to really be awake to see that dynamic behavior, right? That's 50 milliseconds. It's happening quickly for electrical systems. Mechanical systems behave a little bit more slowly. And so 5 time constants takes a while. But in electrical terms, 5 time constants a lot of times is very fast. That's why we talked about infinity in our circuits class. We didn't have to wait forever, did we? It was pretty fast in terms of infinity. Now, what we want to do is try to identify these parameters, alpha and tau, based on somebody giving us this measured data. Do you see that you could go into the lab, hook up a voltage supply, flip the switch, and this capacitor would start charging? And you could measure how fast did it charge and where did it eventually end up. You could collect that data. From that data, you can now build a first-order system, which has an alpha and it has a time constant. That's what we want to do. So let's now look at how we can extract that information. How do we find Y final value? That's what we labeled as A sub 1 in this figure, but if we now had this system and we applied a constant input to that, we want to find an expression in terms of alpha and tau and maybe the amplitude of our constant, what that means in terms of Y sub final value. Do you remember your final value theorem? And the correct answer is your head moving up and down. Yes. 320. A, you definitely did get final value, didn't you? Which is what? The limit as s goes to 0 of s y of s. And that means that we have the limit as s goes to 0 of s, and y of s is the system times the input. And we haven't said yet what the input is other than it's a constant. So let's say that u of s is now the Laplace transform of some constant a for t greater than or equal to 0. What's the Laplace transform of a constant? A over s, right? So now we have all the parts that we need to find an expression for y sub fv. We have g parameterized as alpha over tau s plus 1. We have capital U of s is a over s, so that now we have y sub final value is the limit as s goes to 0 of s times alpha over tau s plus 1, there's our g, times u, which is a over s. We can cancel those two s's. If we let s go to 0, we end up with, what do we have in the denominator? That's the only location where we have an s. Our denominator is well behaved, it's 1, and we now have a alpha, but what was that equal to in our picture? A1. Now do you see that we could compute alpha? We now have one of the pieces to our puzzle of this first order system, and we'll pick up with solving that jigsaw puzzle on Friday.